Very glad to be here and presenting our work on planning bike lanes based on SharingBikes trajectories. This is Jie from Urban Computing Group at Microsoft Research Asia. So as many of you may know that there is actually a bike renaissance in China. Back in the 80s, cycling is the most common used commute mode in China. And as a matter of fact, if you want to get married at that time, you don't need a diamond, but you need a bicycle to convince your in-laws, which I was quite envious about that. Okay, with the rapid development of in China, we have a lot of cars here, which generate a lot of new problems in the city, like the traffic jams, air pollutions. In the most recent year, we have a lot of sharing bike companies like Mobike and Ofo. They are providing a new type of bike sharing system here. By using their system, you can very easily borrow and return a bike, just use your cell phones. So as a result, we're seeing a lot of increase in the bike usage in our major cities. As a result, the government really want to promote this kind of event because it can potentially reduce the air pollution, it can ease the traffic congestions, and it can address the last mile problem in the public transportation systems. And also, riding to work is a much healthier lifestyle. As a result, to promote this riding experience, the most important thing here is to build a very good bike lanes. As we demonstrate in these two short videos, if you are riding your bike on the designated lanes, the experience is good and you are very safe. On the other hand, if you are riding on the road without any designated bike lanes, it is potentially very dangerous and may cause traffic congestions and accidents. And the planning was done many years ago based on the survey and questionnaires. It cannot meet our recent travel demands. That's the reason we try to build a more effective bike lanes for the government. The good news here is that with this new type of services, we have a very good data set here. For example, for the Mobike, we have a large number of users. They will give us very better coverages of the bike usages in the system in the city. For example, we have the Mobike company recently got more than 1 billion users and 25 million daily orders. Also, as we mentioned before, they are stationless deployment. That means you can check in and check out the bike at any arbitrary locations. In this way, we say that there are more realistic travel demands reflected in this data set, unlike the station-based bike sharing systems that you need to go to a station to borrow and return bikes. Finally, these systems try to record the detailed trajectory information for each user. Unlike the station-based bike sharing systems, we only know the check-in and check-out location, station location and time for the riding events. We do not have any idea about how they travel between these two locations. Okay, so I'll give you a brief idea of the dataset we got here. We have a sample dataset from city of Shanghai, and the center here is the Hongqiao Airport. And we have the data for dataset for 1 month and over 13,000 users and as total of 230,000 trajectories. We do some basic statistics based on our dataset we have. We realize that the majority of the users have used this bike for less than 2 kilometers, which exactly is about 1 mile. And also, the majority of the users have used this system for less than 15 minutes because it's about a rough time to go through this 1 mile thing. And very interestingly, we have a certain job at near the 30 minutes mark. This is a result of their billing systems. They charge you one time every 30 minutes. So as the usage temporal distributions, we can see the peaks at the morning and the afternoon rush hours, which means most of the users are using the system for the commute, work-related commute. And finally, we plot the number of distribution of the number of the trajectories at different road segments. We see most of the roads that have very limited number of trajectories, but we do see a lot of significant portion of them have very frequent back usages. So, right now we need to plan our problems. We want to plan the backlengths based on this amazing data. And from the government's perspective, there are some general requirements. First of all, they have their budget constraints for both the money and the space to build the backlengths. And secondly, they want to maximize the utilities for this kind of service because this kind of public service, you want to serve more people. And there's a trade-off between the number of user coverage and their reading length, the coverage of the continuity of their reading length. And finally, it's there's a requirement for the construction and management convenience. For example, if you simply you try to build the backlinks for the top 100 road segments in this area, then you will get a construction plan like this. It's scattered over the space, which is hard to manage when you're doing the constructions. On the contrast, they want to have the result locally clustered. For example, generate k-clustered connect components in a road network. Then we're going to have the problem that how we evaluate the effectiveness of a constructed plan. So we take like a vote from every trajectories. So every trajectory will give a score for the plan we recommended to the government. The score will be given like using these functions. S means the segments this trajectory has been segmented based on the different plans. For example, we have a trajectory here in blue lines. It is segmented into 2 parts in this construction plan, and this is one continuous segment in this plan. So we are trying to give more scores for the plan that covers more continuous length of the user's trajectories. So that's the reason we have this kind of scoring functions. And we have this alpha function to be tunable as a trade-off between the trip coverage and the continuity. For example, if we have a large alpha number, it means we'll give more emphasis on the continuous plan. For example, here, if we have the scores for we calculate scores for these 2 plans. If we have an alpha with a large value, then we will have a better score for plan 2. So essentially, we want to maximize this total score, and with this connectivity and budget constraints, which makes this problem a very NP-hard problem. You can see our proof on the paper. So as a result, we propose a very simple approach. We call it the greedy network expansion algorithm. This algorithm is based on some observations and intuitions from the dataset. For example, the first one is like the spatial hotspots. If we plot a heat map of the back check-in and check-out locations, we notice that there's very high activities around some shopping areas and the subway stations. And another observation is like we check the detailed mobility pattern around these hotspots. So they always have this like star-like patterns. They either origin from one common location and find out to different areas, or they come from different areas and go to the same destination. So the main idea we have for the gradient network expansion is very simple. The first step, you need to select k start locations. This is defined by the government, how many areas you want to build the backpasses, backlanes. After that, you have the candidates from this start location, start road segments. These are the adjacent edges from this in the road network. And for each time, we will choose the edge with the highest score gain per length or per cost based on our score functions. And then we choose the best one to insert into our result set and then put their adjacent edges as the further candidates. And we do this iteratively until our budget is used up. So using these algorithms, the key here is how to select these k start locations. A very naive way to do this one is like we just choose the top k hottest segment on the road network. So we do this first, and we realize we have a very strange result because we want to have 5 clusters, but at the end we only got 1. So we take a deep look at the data set we have. So we realize that if we just simply use the top k method, most of them are connected to each other. This is understandable because there's highly populated residential areas and subway stations and shopping malls and factories around it. People are using these segments consecutively. So as a result, you usually get the top k row segments are connected to each other. So as a result, this will hurt our solution because it limited the searching space and the limited number of candidates we can have to generate the effective backpass plans. As a result, we use another very simple idea to overcome this issue. The idea is like the intuition is like if we just look at the heat map of the riding data here, we notice that there are some rough clusters or rough areas. They should have they are very frequent and very very hot and connect to each other. So we basically select the top M in our system is top 1,000 hottest road segments, and we do a hierarchical-based clustering based on their network distances. And after the clustering is done, and we select the hottest road segment in each cluster as the start locations. In this way, we will avoid the scenario that we have the connected seed or start locations. And finally, we do the greedy expansion algorithms and get our results. So compare these two methods with the same parameters, we can see they have the spatial clustering based algorithm has a better coverage, and to be more specific, we have covered like all 6 subway stations in this area, and compared to the top k-based method, we basically only cover 2 subway stations. And because we noticed that this area is frequently appeared in different solutions and with different parameters, so we take a deep look at it. We go there and we realize we realize the reason we always have this area in the result. This is a terminal station of the subway line 13 in Shanghai. It's Jingyun Road Station, and around it there are very many highly populated residential areas, and also there's a very big shopping mall, Wanda Hongqiao Plaza here. And all these things happens in the radius of 2 kilometers. So as a result, cycling is the most convenient way to either go to the shopping malls or you go to work by trains. So we actually see a lot of bike activities here. And when we arrived there, we saw that the government have already built 2 bike lanes on the major roads. So the riding experience is good because of the designated bike lanes. These two roads is also shown in our experiment results. So we say this also confirm our point that this road segment should have some bike passes. Also on these local roads, the situation is getting worse. For example, there's a lot of illegal parking happens in these areas. For example, here, a car was parked in the bike lane, I guess, and the people have to ride on the sidewalks, which is dangerous and uncomfortable. And this one getting worse because the cars taking all the spaces by the road, and the users have to ride their bike on the main road, which may potentially cause traffic accident. So, as a conclusion, we propose some data-driven approach for urban planning. And we formulate the problems based on the real data set and real constraints from the government. And the techniques we used in this system is very simple, but all of them are based on the inspirations of the data analysis. And we see this is a triple win project for the company, both for the Microsoft and the Mobike, and for the government. And the most importantly, this one is good for the people who are using the bike systems. So we want to do a lot more projects on this as this triple win project. So finally, we want to thank the Mobike company for providing the data set. And we also have a system deployed at this link. And more information can be found on our post sessions. Our post number is 88. Thank you.